Same temperature means same kinetic energy. It doesn't matter what it is. It doesn't matter how much there is. If they are at the same temperature, they have the same kinetic energy, okay? For your number 2, that's how I like to do it. You don't have to do it that way. You could do it in many steps. Whatever works. Can you get out your chapter 4 learning objectives? So let's talk about what's on the test now, because things are starting to layer. By that you mean oxidation. Hydrogen is always -2, except in a process. There's just a minute. Oxygen is -2. Pretty much it, everything else.
I did my homework. Health is so easy. Are we going to go over it? Health.
That's it. Yeah.
It's the other always doing that class. It's coming like a bunch of.
Okay, your test tomorrow is on chapter 4 learning objectives. I think there's 11 of them, so just like your quiz, there's 11 points on it.
-2.
Right.
I don't know why you wrote that. Silly.
Neither. Remember things that are different from the quiz. One is you're going to have to draw a particulate diagram with water molecules, with a dipole, in the right direction. It's in our notes a bunch of times, and in warm-ups a couple times too. Okay? That's going to be a difference. Remember, you cannot use a location as a reason for that question. It's not that much harder, except it uses more words. Okay? Like, there's only so many ways I can say write an ionic equation for. So, like, the basic stuff is going to be the exact same, but the words are going to be more. Okay? And that's tomorrow. If you haven't turned your acid-base titration lab in yet, you can turn it in today if you're ready, but I need that tomorrow.
You guys can calculate the molar mass on the 18th.
Sometimes they give it to you. Most of the time, 90% of the time they will give it. Because it's not a learning objective when they calculate the molar mass. Then they have to put your whole calculation. Your whole calculation in the calculator.
What's that diagram called?
Particles. Oh, one other thing. I gave you a test review. It is buff, colored, and it has like 12 multiple choice questions on it, but I like told you to scribble out 3. Those are the right words. I would strongly suggest if you're going to do anything, because I don't know what your tonight looks like.
Guys, it looks like this.
Thank you. I would do that. Those are the words, and those are the pictures, and those are the things. Those kinds of things are AP stuff. Okay.
Yeah, yeah.
So like the test get harder. The test get harder. Like relative.
No, they get easier.
They get wordier. Content is content.
Is it still like just the same thing as the quiz is just wordy?
It's the same content wordier. So maybe harder to understand what you're supposed to do, but you're doing this. All right. Chapter notes. We're gonna learn chapter 5.
Daisy, where are they? Please, where?
You're pretty cool.
Opposite of E, plus or minus the square root of
2AC minus 4A.
square.
AC.
All over.
4A, 2A, 2B. Such a good life skill to know how to solve the quadratic formula by hand.
You know there's a quadratic formula after your
So much.
Do you know that you just ask Siri
Literally
and
just
she'll tell you?
Or just plug it in.
Do you know that
Just
math is
find
going to
the
be
zero.
useless in the future because all you're ever going to have to add is 2 plus 4. And
Yeah, that's true.
2 plus 4 is
That's
the
true. I've never heard
Hold
of
on,
that.
your calculator. Simple math. Simple math.
I don't know. Chances
And-
numbers in a box that we pull off a different box.
And you always have a calculator. It's not like always. No calculator.
All right, find this page. This is where you're going to start. Talk to somebody next to you about how molecules have potential energy. Ready? Go. Then talk about red things, blue things, long tails, short tails, purple things, and use the word thermal equilibrium in somebody who
Well, okay,
Then
so
with
the
color.
faster it is, the more either.
Then talk about how this picture shows chemistry doing work. Ready, go.
Okay.
I never said I was smarter than you. All right, we're going here and we're drawing two graphs. Find this one, we're going to draw two graphs. We do. I'm not using purple today, but I'm definitely using the red, the green, and the blue. So two graph colors. The huge colors, not the above and beyond colors. Although I kept the purple out if you like to use purple.
This one is like literally nowhere.
Hey, Mason, keep this in color.
Did you find it, Owen? I think it's already one.
No, I'm not talking that.
I gave you a new packet yesterday. You have two packets somewhere.
It was white, like their face.
Okay. Your x-axis is time. Sometimes instead of time, they will say reaction progress, but it means time. Our y-axis is going to be enthalpy. Enthalpy is capital H. Enthalpy is heat, which is Q. They're going to be the same thing as long as our pressure doesn't change. And our pressure is not going to change because we're not going to the moon or below the water. Okay?
What letter is that?
A T for time. So for this top graph, we are going to start off at time 0, so the reaction hasn't started yet, with a high enthalpy. And as the reaction happens, we're going to drop our enthalpy down to here. So our final enthalpy, oops, not delta, just HF, is down here, and our initial enthalpy, HI, is going to be up there. We're going to do the opposite for this bottom graph. At time 0, we're going to start at low enthalpy, and as the reaction happens, we're going to gain enthalpy. So our enthalpy initial is down here, and our enthalpy final is up there. What you're going to do with your battle buddy is label the graphs. Which one is a positive change in enthalpy? Which one's a negative change in enthalpy?
The top is a box.
You can do it.
If we have free time, you can go over there during class, but you guys talk too much, so we don't
I got no point.
All right. If I start off with a lot of enthalpy, and throughout the reaction, I'm losing enthalpy, so system surroundings, the system is losing enthalpy. It can't go to nowhere. It has to go somewhere. Stop. It's going to the surroundings. That would be a negative delta H. We will call that reaction exothermic, releasing heat. We are the surroundings, so it feels hot to us because the system released heat. If we start off low and gain enthalpy throughout the reaction, it's got to come from somewhere. That means it's coming from the surroundings. We call that endothermic. To us, we are the surroundings. To us, it feels cold because we're losing heat. The surroundings lose heat, and that feels cold to us. Okay? Today, what we're going to be doing is spending most of our time talking about calorimetry. Calorimetry is going to be your lab for this. These are just words for things I just said. It's going to be our lab for this unit. Calorimetry is an experiment literally done in a coffee cup. Like, for real, in a coffee cup, I go to pick a tape by coffee cups. We put two in front of each other, just or beside each other to help with insulation. The top is perfect because our temperature probe fits right in here, and we can be next Wednesday, okay? Just if you like to plan ahead. When we take the temperature, we are not taking the temperature of the system. We can never measure the system. We can only measure the surroundings. Yes.
Is Wednesday the 16th?
I don't know.
Good question. Yes.
Let's say the 8th and it's Tuesday, so plus 8, 16, yeah.
Why? So that's the PSA.
Oh, so let's
We'll be
not do it
back.
Wednesday.
Oh.
Oh, you guys will be back.
Yeah.
But other hours, first and third hour.
But it's only juniors, right? And only like half of you are juniors, so they can do it during Christmas. I don't know. I'll get back to you.
Aren't we doing the left?
No, I want to teach you Friday.
Yeah.
Okay. Calorimetry is how we measure heat flow by using temperature. Remember, we do not have a joulometer. We have a thermometer, so I can say where the heat is going. Is it going into the system or is it going into the surroundings? But we're going to have to calculate heat, and a calorimeter gives us that data. Okay? The equation that we're going to be using, I swore that you guys used this before, but then somebody told me no. Q equals MCS delta T. Q stands for heat. Heat is enthalpy as long as our pressure doesn't change. The unit for energy is joules. This is going to come out in joules. N stands for mass. Mass has to be in grams. CS stands for specific heat. Now this is where reading comprehension is important details. Most of the time the unit is joules over grams degrees Celsius. Most of the time. Sometimes though it's joules per grams Kelvin. Kelvin is just another unit for temperature. Gotta pay attention. Sometimes it's joules per mole degrees Celsius. So instead of plugging grams in, you're going to have to plug moles in. And I'm going to show you a sample problem just to remind you of that. Change in temperature is always our final temperature. Any kind of change is final minus initial, whether it's in Kelvin or degrees Celsius. Actually doesn't matter because when you subtract them, you get the same value. Okay? So more on specific heat. Specific heat is how much energy is in joules, it takes to raise the temperature of 1 gram of something up 1 degree Celsius. If I had 1 gram of it, how many joules of energy do I have to put into it for just to go up 1 degree? Okay. Water has a very high specific heat at 4.184 joules per grams degrees Celsius. Like way higher than most things. Just in a sentence, that means it takes 4.184 joules to raise a milliliter is a gram up 1 degree Celsius. That's a lot of energy, which is why it takes so long to boil water. And that has to do with the intermolecular forces because water is such a strong magnet. It's really happy being like this. It doesn't want to do liquid molecule. Okay. Compare it though to aluminum. Aluminum foil. Aluminum foil is 0.90 joules per grams degrees Celsius. Did you ever, okay, maybe you haven't experienced this, but maybe you have. Like if you're making lasagna or like egg bake or something, and your mom or dad or whoever does cookie puts aluminum foil over the top of it, puts in the oven, and then you take it out of the oven, you can pull the aluminum foil off right away. It is not hot. That's because it has a very, very low specific heat. It takes very little energy to heat it up. but that means it takes very little energy to cool it off. It goes right out of the system into the surroundings. So by the time you take it out and set it up, it's already cooled off. But that's not true for water. It takes a long, long, long time, okay, for it to cool off. Yes?
Is like the joules per gram degree Celsius, is that linear? Like, is it the same to raise 100 to 101 as like 0 to 1?
Yeah, it's a conversion factor. Direct. Okay, when the music starts, talk about how come when I heat up a plate of leftovers, it doesn't all heat evenly. Ready, go.
Because some stuff is so higher. And because it doesn't completely sugar it.
No, it's because of the water
I
content.
didn't get those notes today.
The parts of it that are super watery will take longer, but like other parts will heat up faster. So that's how you gotta always stir it, and then it distributes the heat. Got it. A fuel is burned in a cylinder equipped with a piston. The initial volume of the cylinder is 0.25 liters, and the final volume is 0.98. Reading comprehension, that means that the piston moved up, because now it's up here for it to be 0.98, okay? If the piston expands against a constant pressure, so that's atmospheric pressure, that's the gas molecules pushing down on it, at 1.35 atm, how much work in joules is done? Work equals negative P delta V. So work equals negative pressure in ATMs, 1.35. Delta is always final minus initial, so 0.98 minus 0.25. It's going to come out in a unit called a liter atmosphere. It needs to be in joules. You're going to have to do a conversion. Push your buttons and then push your buttons. Ready, go. Give means that it's released into the surroundings. So that means that the system lost 99.8 joules to the surroundings because it's not magic, it has to.
I didn't get that answer.
I think I'm right. Thanks. Okay. Did we do number 10 yesterday? Can you look at number 10? Did we do that one yesterday? No. Okay, we're going to do number 10.
Yeah.
It just depends. Like, if I probably kept all the decimals and just a decimal one. Then maybe I didn't. Like, you did something. Number 10 is the same as number 8. With your battle buddy, reading comprehension, figure it out. Number 10 is the same as number 8. Ready, go.
Oh, this is light work. Yeah, you did that. See, if you.
How much heat is Q, is needed to warm 250 grams of water, which is a cup, from 22 degrees Celsius, which is room temperature, to 98, which is almost boiling. Q equals MCS delta T. Q is going to come out in joules. We have 250 grams. The specific heat for pure water is 4.184 joules per grams degrees Celsius. 4.184. Our change in temperature is always going to be our our final minus our initial, so 98 minus 22. It's going to come out in joules. You're going to have to scoochie back 3 to get it to kilojoules. It needs to be in kilojoules. Push your buttons, push your buttons.
Are we going to have that conversion on?
Yeah. Like, you're going to have to know how to do it.
No, like, are we going to have? I'll beat you in the press. All right, good. Oh, yeah. I'll beat you in any potential.
Okay. When a student mixes 50 milliliters of 1 molar hydrochloric acid with 50 milliliters of 1 molar sodium hydroxide. We know they're making salt water. I have 50 milliliters, it's 1 molar. I have 50 milliliters, it's 1 molar. In a coffee cup calorimeter, the temperature of the resultant solution increases from 21 to 27.5. Calculate the enthalpy change. It doesn't say calculate the heat. It says calculate the enthalpy change for the reaction in kilojoules per mole. I'm using these colors on purpose. Enthalpy change is equal to our kilojoules divided by our moles. We don't have either of those numbers, so we're going to have to solve for both of those and then divide it out. Reading comprehension. Assuming the calorimeter loses a negligible quantity of heat. When we do an experiment in a coffee cup, we're making the assumption that all the heat from the system is released into the water, and I'm measuring it. But it's kind of a big assumption because the cup is going to stop. The cup is stopped. The cup is going to absorb some of the heat, right? Not all the heat is going to stop. Make the water hotter, okay? So it's going to give you a line like that, and it just means you can ignore that. The total volume is 100, the density is 1, and the specific heat. So the first thing we're going to do is we're going to solve for that kilojoules part. We already learned how to solve for kilojoules. Q equals MCS delta T. We do not have a mass, though. We have 50 milliliters plus 50 milliliters equals 100 milliliters. And the density of water is 1 gram per milliliter. So that means that it's going to weigh 100 grams. So now I know Q equals 100. The specific heat of an aqueous solution is 4.18. The specific heat of pure water is 4.184. Aqueous is 4.18. When I say go, tell somebody next to you. There's 2 different specific heats. Ready, go. That you do kind of have to know. Our change in temperature is 27.5 minus 21. That's going to come out in joules. Scoot you back 3 to get to kilojoules. Push your buttons, push your buttons. Ready, go. Why is it negative? Reading comprehension. It's getting hotter, but what's getting hotter? The surroundings are getting hotter. I cannot measure the system. I can only measure the timing. So if the surroundings are getting hotter, that means it was an exothermic reaction. My enthalpy change has to be negative. Another way to think about it is this math is for the surroundings. So it's going to be the opposite of the system because the system has to lose it. Don't flip your temperature though, final minus initial, because if it was endothermic, then it would turn out to be positive. All right, green, moles. Good thing you have a test tomorrow, and you just did a warm-up problem on how to solve for moles when we have molarity. It tells us moles of HCl, so I'm going to use my moles of HCl stuff. I like to do it this way. You don't have to. I go 50 milliliters over 1 times in a line. Milliliters on top means milliliters on bottom. There's 1,000 milliliters in a liter, and in 1 liter there's 0.1 moles. Or was it 1.0? 1.0, thank you.
Let's go. Go crazy.
Does not answer our question. Our question says, what is the enthalpy change? Enthalpy change is our kilojoules, negative 2.7 per per mole, 0.05. Go ahead and push the buttons. Kilojoules per mole. That means that the system lost 54 kilojoules for every mole of HCl. With your battle buddy. Now do it again. Do it on number 15. Ready? Go. Reading comprehension.